My name is Kyaw, student number 189165880. This presentation is for Assessment 3, MAA402 Advanced Applied Architectural Systems. My case study is Building 215 of Cardiff University. Its location is 12 Ridley Walk, Bentley, WA 6102. My role is to study energy. The objectives of the study are: first, to identify the environmental and technological systems of the case study building. Second, to develop a new envelope for the case study building. That is, to use an energy analysis tool to test the existing envelope and the new envelope. Environmental system is the climate and weather. Technological system of a building is everything that makes the building. The building is architectonic components designed and put together by the architects and engineers for human occupation. Technological system must be able to withstand against undesirable effects and to use the desirable effects of the environmental system. Perth is in climate zone 5, warm temperate. The first stage is to identify the environmental and technological systems of the case study building. The case study building has two halves. The eastern half has 4 levels built with high thermal mass, that is concrete. The walls are concrete and the roof is concrete too. High thermal mass slows down temperature passing through it because it only gains or loses temperature very slowly depending on its thickness. That effect keeps the interior temperature stable. In hot summer, humans perceive that interior temperature as coolness. In cold winter, humans can perceive it as warmth. Classrooms are located in eastern half. This part is highly insulated too. Both exterior walls and interior walls are insulated. It has only a few windows. Daylight and passive ventilations are very limited. It relies on artificial lighting and a large HVAC system, which is located on level 4. The design emphasizes on keeping the interior cool. Level 4 roof provides extra cooling. The coldest level might be level 2 or 1. The interior walls are curvy. That seems to deal with acoustic performance. The building seems to be cold in southeast area. This place could be good for summer. The western half is an atrium. Its envelope is metal. The walls are metal and the roof is also metal, which is suitable for widespan. The atrium is highly glazed and light can enter from west, north and south. During day hours, temperature in the atrium seems to be comfortable. However, it must be very cool at night. There are concrete bridges in the atrium to connect with other buildings. There is an elevator. The second stage is to develop a new envelope. The role of architecture in energy conservation is to design building envelopes that will provide maximum comfort to the occupants without unsustainable amount of fuel consumption. This is done using the right amount of the suitable material such as high thermal mass, insulation, and various strategies could reduce fuel consumption. Zero net energy buildings became popular because they only require energy that can be produced on site or within their boundaries. That is to install solar PVs, wind turbines, and other renewable energy technology. Large buildings do not have enough space to produce energy on site. They should be designed with passive heating, passive cooling, and passive ventilation systems that would optimize them to perform. Buildings 215 might have enough space for site energy. To develop a new envelope for the case study building, several precedents were chosen based on IN lectures that explain about troop wall, water wall, and smart glass. These precedents are supposed to be located in Western Australia. However, buildings with troop walls do not have images online. They exist, however, their whereabouts are unclear. Books only explain about how to use troop walls in Australia. I was forced to search for a few precedents that exist in similar climates. My research found different types of troop walls. One of them is transwall, which is made of glass and water. Transwall is chosen for new envelope because I was convinced it would provide something good. However, I could not find any precedents that have transwall. To imitate transwall, I developed a troop wall design. It has water, transparent glass, and transparent acrylic plastic. Glass sheets and acrylic sheets are 50 mm thick nominally. They may be thinner as long as they can support the water. Troop wall is combined with water wall, so I call it water troop wall. They are good for preventing noise that is passing through them. But the glass must be covered with transparent acoustic film. The water can cool down sunlight. Acrylic or plastic panel acts as insulation, so the atrium has proper temperature and daylight. The acrylic and glass panel should be as transparent as possible. Water troop walls need structural support. Smart glass could be used in curtain walls. For assessment 3, I have improved the envelope design. The strategy to gain low EUI in the new envelope is very simple. Allow sunlight to reach the interior with some heat. When the interior is overheated, it's time to use passive ventilation. Windows added to certain walls and the eastern sides of the building. The southern exterior walls are sandwich panels. Water troop walls are supported by concrete slabs and concrete walls that also support the concrete roof, gutter, and downpipe. Roof slope is 10 degrees. That is good for solar PVs and collecting rain. A rainwater treatment facility is located under the balcony. There is a well for overflow. When water tank is fully filled by rainwater, the overflow can go into the well directly or after filters. The well could be used for cooling warm air from outside. In summer, cooling and ventilation can be achieved by pumping fresh air from outside into the well and forcing the cool air inside the well to enter the building. This strategy is adopted from Kyaw dome. To create the slope, the roof was redesigned and level 4 was moved to the southern side. Level 4 is being used as the space for HVAC system. In new design, this HVAC system is no longer required. The new system recommended by Insight is ASHRAE package terminal heat pump. Both new roof and level 4 are concrete to provide long-term structural integrity and fireproofing. If solar panels are installed, level 4 can be used as a battery room that must be fireproof. A new veranda was added to eastern side to provide space for relaxation. This is an aesthetic purpose as well. To climb the roof, the elevator is increased to level 4. This is needed for installing and maintaining the PVs. Concrete roof is heavy, so columns were added to support them. The western side has a sculpture to provide aesthetic quality once the sculpture is created by sun. Air inside will rise. If linked to interior spaces with copper pipes, passive ventilation could be created. Warm air inside the sculpture could be pumped into cool areas. If this strategy is not used, the sculpture can be smaller. The third is to use an energy analysis tool to test the existing envelope and the new envelope. I tested these two models in Autodesk Insight Analysis software. This tool analyzes the models of existing or conceptual buildings to explain how their designs consume energy to meet maximum performance to provide human comfort inside these models. The software does not know or able to analyze all strategies that could possibly be used in these buildings. Based on the drawing files provided by Curtin University, I developed a Revit model of Building 215. Based on that model, I developed a new envelope. I provided these two models to my group. The results are 301 kilowatt hour meter square per year is the EUI of the original envelope. 236 kilowatt hour meter square per year is the EUI of the new envelope. The new envelope gets slightly better EUI. Energy use intensity, EUI, is the amount of energy needed by a building to function and to keep the interior at the temperature in which humans feel comfortable. This is called comfort zone. The temperature range between 18 degrees Celsius and 25 degrees Celsius. The software also calculates PV surface. If the roof has slope, the EUI could change. After calculating the PV surface, the EUI of the original building does not change because the roof is flat. However, a deck can be built on the roof to support PVs. On the rooftop, that envelope has a few PVs. Its roof design is not suitable for many PVs. After PV surface is calculated, the EUI of the new envelope is 193 kilowatt hour meter square per year. Water-thrown walls need water. Without water, EUI increases. With water, EUI decreases about -9 kilowatt hour per meter square per year. The test shows skylights can reduce EUI. More daylight and solar gain seem to improve building performance. The main reasons in achieving low EUI are water-thrown walls, Water is able to cool down the sunlight, while transparent glass and transparent acrylic allow sunlight to pass. The acrylic and glass panel should be as transparent as possible. Acrylic sheets act as insulation. The walls that support water-thrown walls act as a shading device. Windows provide daylight and passive ventilation. There are many windows added around the building. Skylights were added to provide more daylight and solar gain. More high thermal mass. More high thermal mass to the roof and the webs. These webs provide some shade. 10 degrees slope for the roof. The ultimate slope for part is 10 degrees. I believe this new envelope will improve the performance of building 215. Thank you very much for listening.